All right, we've learned a lot about how to solve first-order ODEs. We've talked about first-order ODEs in the linear case. You use the integration factor. It always works. If it's nonlinear, then you should first check if the equation is separable. If so, you just directly integrate like we showed last time. Now today, we're going to start with understanding if it's a first-order ODE, if it's nonlinear and not separable. It seems like you're going down this path of further and further discouragement. It's nonlinear. Ugh. It's not separable. Ugh. You have one more thing you can check. And that thing is the equation exact? If the equation's exact, then there is a special technique that we can use to make it solvable. So we're going to work on that today. First-order ODEs, nonlinear, not separable, exact. How do we make the solution work? Let's get started. If we have a first-order, nonlinear, non-separable ODE, there is one check we should do to see if we can solve the equation. And that is the concept of exactness. Now, before understanding what exactness actually means, let's first consider the generic first-order, nonlinear, non-separable form, which can be written in the following way. We have some function n, which is going to be a function of x and y, dy dx. The function you want is y, depends on x. M, which is another function of x and y. Now, we can't conveniently manipulate the function of x and a function of y into a separable form. So this is the best we can do, and we can keep the equation in this generic form. Now, at this stage, you're probably getting an idea of how to solve differential equations. We solve differential equations by guessing. I'm sorry, that's just the way we solve differential equations. You make a good guess, you see if the guess works, or you make it work, and you move forward. So we're going to do the same thing here. We're going to make a guess about the nature of n and m, and see if we can define exactness through this guess. So suppose there is some function phi, which is defined in the following way. Suppose there's some function phi, which is a function of x and y, your independent and dependent variable, such that the partial derivative of this function phi with respect to y is equal to n, which is the first function we defined earlier in front of the dy dx. And the same function phi has another property, which is if you take the partial derivative with respect to x, then that is equal to the other function over here, m, which is a function of x and y. Okay, let's just suppose that such a function really exists. Again, we solve differential equations by guessing. So we're going to make a guess that there is some function out there, phi, that has these two properties. Let's consider next what happens when you take the mixed partial derivatives of each of these conditions. So let's write that down. So what I've done here is to take the partial derivative of this first condition with respect to x, and another side, d phi dx, but this time we take the partial derivative with respect to y. Now, when you compare these two terms, we like to ask the question, is this equality true? Is it true that I can take the second derivative of the function phi with respect to x and then y in that order versus the second derivative where you flip the order of differentiation? I've made a typo here. Let me fix that. Of course, it should be with respect to x. right? We've brought down this left-hand side down here, this right-hand side straight down here. So the question is, when you flip the order of the partial differentiation, is it true that you can just freely swap them? Now, it turns out that this is true. The two things are equal to each other if and only if this function phi that we've posited that exists is continuous along the real number line. If that is true, then this condition is always satisfied. So I'm going to remove the question mark because this condition is true if phi is continuous along the real number line space. And this is called Clairaut's theorem. You might have learned that in your calculus class, but let me just write that down. This is Clairaut's theorem. And let's make one more step where we map our definition of these partial derivatives with n and m and stick it into this Clairaut's theorem and see what happens. So I'm using Clairaut's theorem, or just rewritten up here. Of course, partial phi, partial y is our definition for n. Partial phi, partial x is our definition for m, back from earlier. And this is our definition of exactness. An ODE is exact if and only if, IFF, if and only if, partial n, partial x is equal to partial m, partial y. If this is true, then this ODE is defined to be exact. And as you will see next, if the ODE is exact, you can make a lot of progress in actually solving this equation. Let's see what happens and how we can use the definition of exactness to make progress. I've cleared some space so that we can continue from our original generic form and see how this function phi can help us make progress. So all I've done is here I've rewritten our generic form by multiplying across by the small increment dx. Otherwise, I've made no other changes. Let's substitute our definition for n and m with respect to the partial derivatives of phi. You get something like this. Just replaced n and m with the partial derivatives with respect to phi. Now, when you look at the left-hand side, this is the definition of the total derivative of phi. This is the total derivative of phi. We often see this in thermodynamics. Whenever you have some differential of an internal free energy or a Gibbs free energy, dg is equal to negative partial g partial t dt plus blah, blah, blah. You're taking the partial derivative of a function, holding fixed the other variable, and multiplying it across with the small increment dt, or d volume, or d pressure. Right? It's the same thing. So you can rewrite this whole left-hand side as the differential of d. And that thing must be equal to 0. So what this means is that if we integrate both sides, you're just left with the function phi on the left-hand side must be equal to a constant of integration that pops outside. Just like that. So we've just shown you that this sum function phi that we defined earlier apparently is at best some constant. A constant of integration that comes out as a result of this final integral. And I'm just going to call that constant c. So at this stage, we've made a lot of progress. You may not know it, but we have everything we need to actually solve our differential equation. So let's think a little bit about the definition of phi, and we have more information about phi at this point. We have two definitions for n and m. We have first partial phi partial y is equal to n. That's our definition from up here. That's how we define the function phi. And d phi dx is equal to m. I'm just multiplying across by the small increment dy or dx to write it in this form downstairs. So presumably, this function phi must satisfy this equation and overall be equal to a constant. So now I could just integrate both sides, just like that, and you end up with the following form. And you get these two forms. First, on the left, you have your function phi, which is a function of x and y, is equal to the integral of n with respect to dy, plus some constant of integration, f, as some function of x, right? Because here, we're integrating with respect to y of a multivariable function n. So in general, you'll be left with a constant of integration, which could be a function of x. Same thing on the right-hand side. We have the same function phi, which is an integral of m with respect to dx, and therefore, you can have a constant of integration with respect to y. Okay? And apparently, according to what we derived here from the generic form, both of these on the right-hand side must be equal to a constant. They must be the same quantity, even though n and m are different, and you're integrating with respect to different variables. When you sum everything together on each side, they must both be equal to c, the constant, and the same constant. So this is it. You may not still see it, but this is all we need in our approach to actually be able to solve this equation. So let's move on to a step-by-step of how you would use this approach to figure out the solution to the differential equation. And then we'll do an example. Once you see the example, you'll see exactly how all of this ends up fitting together and how this helps you solve the differential equation. I've written here a step-by-step instructions of how to use this exactness procedure to solve first-order, nonlinear, non-separable ODEs. Step 1, rewrite your generic ODE as the form shown here. N dy plus m dx equal to 0. That's step 1. Step 2, check for exactness. And now you know what the definition of exactness means. You take the partial of n with respect to x, partial of m with respect to y. If they are equal to each other, great. The equation is exact. You keep going. Proceed to step 3. If not, it's really disappointing, because if not, most of the times you can't use this procedure anymore. There are situations where you can massage the equations to make it exact, but it doesn't always work. So generally, you want this to be true so that you can keep going. Let's work on those cases for now. Step 3 is you suppose that there exists a function phi that's equal to a constant, c. And you have two relations for your phi. One is the integral for n, one is the integral for m. And you know, based on our derivation from earlier, that both of these functions are equal to each other and equal to the constant c. So both are equal to c. Step 4, you perform the integrals for n and m, and you apply initial conditions, IC, or boundary condition, BC, depending on the nature of the problem you're working on. You'll be supplied with some kind of constraint that will tell you the value of c. It's constant of integration. Finally, optionally, you can solve for your function y as a function of x. And there you have it. You have y as a function of x. That is ultimately what you want. You have an ODE. Your goal is to find the function you want, which is y, as some function of x, your independent variable. And you're completely done. OK, so even with these 5 steps, I know a lot of you are still kind of confused. You can't really see how it actually comes together. All right, let's do an example. Once we do an example, you'll see all of this come together and how you might be able to use this for a variety of ODEs that fit this particular classification. Let's do an example. You have a constraint, y at x equal to 1 is equal to 2. Now, when you look at this equation, first you should try to classify it. It's a first order equation because you have this dy dx term as their highest order derivative. It's an ODE. It's nonlinear because you have this y squared term. So it's a nonlinear differential equation. And lastly, if you just stare at this equation long enough, you'll realize that you can't separate it. You can't put all the y's onto one side of the equation and all the x's onto the other. You can't. You try to do it, you can't. You can't, this 2 plus x squared y means that you can't put a part of this on one side and all the y. It just won't work out. So this is an example of a first order, nonlinear, non-separable ODE. So we're going to carry out the 5 steps. Step 1 is to rewrite the ODE in this form. So in this particular example, it's actually not that much work. All you have to do is multiply across by the small element dx. So let's do that. All right, we've completed step 1. We've rewritten it in the way that we should, and we can define our n function and our m function following the form that we've written over here on step number 1. Now, moving on to step number 2. Is the equation exact? Let's check it out. So all we need to do is check the partial derivatives. Okay, so I've just taken the partial derivative of n and m with respect to x and y. Very easy calculation. You just get 2xy to drop out on the left. And on the right, you also get 2xy to drop out. Therefore, you can confirm that this relationship is true and the equation is exact. Great! Smiley face, we can make progress. Awesome. So we keep going. Go to step 3. We suppose there is some function phi, which is equal to a constant that is given by these 2 relations. Let's write those down. All right, we're now performing step number 3. We've supposed that such a function phi exists based on our exactness that we've verified. Now we just plug in the n to this integral over here. So we have this integral over dy of the function n from our definition of n. And we have the other integral over the function m, xy squared, with respect to dx. You perform those 2 integrals. On the top, you get 2y plus 1/2 x times y quantity squared plus some function of x. On the bottom, you get 1/2 xy quantity squared plus g as some function of y. Now, remember that both of these phis are the same function. It's the same thing, and they must be equal to each other. So, when you look at the top equation and the bottom equation down here, as of now, they're not really looking the same. The top equation has 2y and then this other 1/2 term. The bottom one has this 1/2 term, but no 2y. But we have this g of y, which we can find and select what it should be to ensure that these 2 functions are the same. So at this point, we match like terms to make it, to force it, so that this function phi and this phi down here give you the exact same form at the end. So what I've done here is to say that f of x must be equal to 0 because down here, there is nothing that the top equation is missing in order to match with the bottom. In fact, if you had some other function of x up here that didn't appear down here, that would be a problem, because now you have an inconsistency. The same function not being equal to each other. You can't have that. Whereas on the bottom one, this g of y makes sure that we capture the missing term 2y up here. So we're going to use this free function g of y to match the term that the bottom equation is missing, which in this case is simply equal to 2y. That's the term that we're missing down here that we have in the top equation. Now, with this selection of f of x and g of y, the two equations, the two solutions for phi, are identical to each other, which it must be the case. So at this stage, we have our solution for phi. This is step number 3-ish, 4-ish. We've made a lot of progress. So apparently, our function phi, based on matching like terms, is simply equal to 2y plus 1/2 xy quantity squared. And again, that must be equal to a constant. So this is our solution to the differential equation. Just like this, we have an equation that relates y, which is the function you want, to x, which is our independent variable. Now, the last thing we need to do is apply initial conditions and boundary conditions. In this particular case, we're given as a constraint that at position x equal to 1, the value of y is equal to 2. So all we need to do is plug in those numbers to figure out what the constant c is. And there you have it. All we've done is to use the constraint y of 1 is equal to 2. So you plug in 2 times 2 plus 1/2 1 times 2 quantity squared. That gives you the constant c on the right-hand side, which is equal to 6. Therefore, this very bottom equation down here is it. This is your solution to the first-order, non-separable, nonlinear ODE. Now, you could do an extra step. I said earlier it's an optional step 5 of solving for y as some function of x. And clearly you know how to do that. This is just a quadratic equation for y. So you use the quadratic formula, negative b plus or minus square root of la la la. And then you can literally write this equation as y as some function of x, which is what you've always been doing with solutions to differential equations. You have a differential equation of y, which is the function you want, as some function of x. Ultimately, you can do that. Now, I'm just going to leave this solution in implicit form, where I just leave it as y not solved as a function of x. So we're just going to leave it in implicit form. But if you wanted to do that, you can take the extra step. In many situations, leaving it in implicit form is perfectly okay, and actually sometimes more illuminating than trying to solve some crazy radical exponential solution. So this is it. Hopefully this example gave you a step-by-step understanding of what are the 4 or 4 plus 1, 5, fifth optional step that one should take for solving a first-order, nonlinear, not separable ODE. So that completely concludes everything you need to know about solving first-order ODEs. Now, moving on to next time, we're going to start a chapter on second-order ODEs. So, see you next time.